Good evening to all, and welcome to another session of the NPTEL course Heat Transfer. So today we'll be discussing the week 12 topic, which is basically the heat exchangers. So heat exchanger is one of the practical thermal device which you can find it almost everywhere. So ranging from the uh, air conditioning unit to the power plants, you can everywhere you can find the heat exchanger. Heat exchanger is basically a device which transfers heat between two fluids which is at a different temperature uh, uh, between a solid one. So today we will be discussing some of the practice problems related to the topic heat exchangers. Okay. So today we'll get started with the first question. So we have the LMTD of a counterflow heat exchanger is given as 20 degrees Celsius. The cold fluid enters at 20 degree and the hot fluid enters at 100 degrees. Okay. The mass flow rate of the cold fluid is twice that of the hot fluid. The specific heat at constant pressure of the hot fluid is also twice that of the cold fluid. So these are the given things. It's given in the question. So you have to find out what is the exit temperature of the cold fluid. So I'll give you some time to solve. After that, I will start. Okay, the given data, the LMTD is given. I'm representing as delta Tm is 20 degrees Celsius, and the hot fluid enters at cold fluid, that is TCI, is given as 20 degrees Celsius, and hot fluid, that is THI, is given as 100 degrees Celsius, and the mass flow rate of the uh, cold fluid, that is given as twice that of mass flow rate of hot fluid, and the specific heat, that is Cp of hot fluid, is twice that of Cp of cold fluid. Okay, so these are the basic given data, and you are asked to find out what is the exit temperature, that is TCO of the fluid. Okay, so have we got the answer?
Yeah, I'm making an equation that we will be getting the equations. One is from the LMTD, we will be getting one equation, and when we will be getting one equation from the heat balance.
Yeah. So the hot fluid is entering at 100 degrees Celsius, and cold fluid This is THO and this is TCO. So we are asked to find out this one. What is this TCO? So please solve it and give the answer. Have you got the answer?
No, sir.
Okay, so first we will do the heat balance, which is the heat gained by the cold fluid is equal to the heat gained by the hot fluid. Can you please mute? Yeah. So MHCpH THO minus THI minus THO will be equal to MCCpC TCO minus TCI. Okay. So as it's given MC is 2 times MH and CPH is 2 times CPC. Okay. If you convert to uh, any of this, I'm converting to CP. So the specific heat capacities, so the heat capacities both cancel out. Okay. It's same. So we'll get THI minus THO is equal to TCO minus TCI. Or we can write, so this is one equation number one. This is the first conclusion we have get. So this is like a special case. So where the both fluids have the same capacities, heat capacity. Okay. So what is LMTD? So LMTD here, if I say this as THI and TCI, so delta Ti minus delta To divided by ln delta Ti by delta To. So, so if I write this, what is delta Ti? The inlet is Thi minus Tco. Okay. And delta To is Tho minus Tci. So from this equation, if you rearrange, you will get Thi minus Tco. I am taking this here and Tho minus Tci So this becomes same. So THI is should be equal to TCO. So this LMTD is not defined. You have to, in this case, your LMTD is not defined. So you have to differentiate. So this is a special case. At this, under this condition, TCHI is equal to THO. Okay. So in this case, the LMTD is not defined. So we have to take the L hospitals rule and all. So the derivations we can refer back to the textbooks. So under this case where the LMTD is not defined, so this is the LMTD, that is either delta Ti or delta To is the LMTD. Under this special case only, I think maybe you have got stuck in this portion. So then already delta Tm is given. So what is delta T? What we have to find out? TCO. So THI minus TCO. So which is equal to THI already given 100. So minus TCO, that is TCO is equal to 100 minus 20 is equal to 80 degrees. So 80 degrees Celsius is the exit temperature of the cold food. So let's move on to the next question. So in this question we have a
Sir, in this question, that is there hospitals rule? One rule is there that hospitals rule. Is that valid here?
no, that is from mathematics. It's very when we have non-defined in both the cases, 0 by 0 cases, we will differentiate the numerator and denominator. That's from differentiation in mathematics.
Sir, that your sound is really not clear that now. I don't know why.
Actually, it's from a help hospitals rule. It's like when the numerator and denominator are not defined, so we will take the derivative of both. So that is the thing. You can refer back to a textbook. It's just a mathematics, not a heat transfer. So,
Sir, there is a problem in your sound actually. That this sound is not clear.
actually, I don't know. I am using the same thing. Maybe it may there may be some internet problem.
Okay.
So we'll go to the next question. So in a condenser, water enters at 30 degrees Celsius and flows at a rate of 1500 kilogram per hour. The condenser is at a temperature of 120 degrees Celsius and cooling water leaves the condenser at 80 degrees Celsius. If the overall heat transfer coefficient is 2000 watt per meter square Kelvin, the heat transfer area. So we have to find out the heat transfer area of the condenser. In this question, we basically have a heat exchanger. Okay. So the steam is condensing, sorry, the water enters at 30 degrees Celsius and the flows at a rate of mass flow rate of water 1500 kilogram per hour. Okay. The condenser, the condenser is at a temperature and the cooling water leaves at 80 degrees. So the condenser surface is maintained at same temperature, which is at 120 degrees Celsius. Okay. Uh, the overall heat transfer coefficient is given as 2000 watt per meter square Kelvin, and we have to find out the heat transfer area of the uh, condenser. It is basically like we have a tube, so you can just imagine. So water is entering, and some condensation is happening outside the tube, so that it's maintaining at 120 degrees Celsius. And the cold water is entering and leaving, and it is taking up heat. So this is also a kind of heat exchanger. First, we will find out the LMTD, that is delta Ti is equal to how much? 120 minus 30, which is equal to 90 degrees Celsius, and delta To is equal to 120 minus 80, which is equal to 40 degrees Celsius. So what is the LMTD? Delta Ti minus delta To divided by ln delta Ti by delta To is equal to 90 minus 40 divided by ln 90 by 40. So what is this answer? What is the LMTD?
61.7.
61.7 degrees Celsius. So what is Q? This is MCP delta T is equal to the overall heat transfer coefficient, area of surface area, and LMT. So what we are asked to find out is AS is equal to M water Cp delta T divided by U0 T. So what is the mass flow rate of water? So to convert it into kilogram per second, 1500 divided by 2600 Cp. Cp you can take as 4127. What is the temperature difference? 80 minus 30, which is 50, divided by the heat transfer coefficient is given. Overall heat transfer 2000 into 61.7. So what is this answer? Can you please find it?
7.1.
7 point. How much?
7.1.
7.1. Okay, let me
B,
check
B is
that.
the answer.
Okay, let me check that. I am getting point 0.7. Okay, let me calculate once more.
Actually, I use her value 4.2, 4200, that specific heat of water.
That is kilojoule. Huh? So you have to convert to joule.
Yeah, 4200 I have used, and then I
Uh,
got the answer 7.1.
okay, let me see.
B.
Actually, I am getting point 0.7. You please check your, you calculate this once again and let me check.
So I think it is you, point 0.7.
Yeah, point 0.7 meters square. That is a heat transfer area.
Okay.
Let's move on to the next question. So we have a condenser of a steam power plant which contains 1,000 brass tubes of thermal conductivity given of each of inner and outer diameter also given. Steam condensation happens at the outer surface of the tube is characterized by a convection coefficient of 10,000 watt per meter per Kelvin. If cooling water from a lake is pumped through the condenser tube at 4,000 kilogram per 400 kilogram per second, if after extended operation a fouling resistance of this much is happened at the inner surface, what is the overall heat transfer coefficient based on the outer surface area? That is the question. So I hope you understood the question. So we have a condenser of a steam power plant which has 1,000 brass tubes, and through the brass tubes we have water is flowing, and surface uh, outside surface steam is condensing, and the convection coefficient condensation the heat transfer coefficient is also given at the outer side, and also and because of the extended operation the fouling or the scaling takes place at the inner side of the tube. So because of that, a resistance will be developed for the heat transfer, and that fouling resistance is already given. So you have to find out what is the overall heat transfer coefficient based on the outer surface area.
So that tube arrangement is not required here.
Tube arrangement in the sense, no, it's not the what is the condensation. You are asked to find out uh, the outer overall heat transfer coefficient of the tube with the outer surface. It's like a what to say. Uh, the previous case, similar to previous case, but here it is 1,000. Here it has some bulk tube and some fouling resistance, and also you have to consider the thermal conductor or the conduction resistance of the tube. That's all. It's not a condensation heat transfer. It's already given 10,000 watt per meter. So the arrangement is not required. Okay, so here we have a tube. I'm just taking a single tube out of 10,000 tubes. It's a brass tube. Okay, and the outer dia is given 28 mm, and inner dia is given 25 mm, and the thermal conductivity is given. Okay, so if you write the what to say, the resistance equal to UA. So I am, as it is asked, based on the inner surface area, sorry, the outer surface area. So I will be taking this one by HAI plus. This is the fouling resistance plus Ln by Di. This is the conduction resistance 2 pi KL plus 1 by HOAO. So as we are asked to find out UO, by multiplying the entire thing with AO, which is AO is equal to pi DOL. So 1 by UO is equal to uh, 1 by HI DI by D, sorry, DO by DI.
But sir, here HI is not given in the data.
We have to find out.
Pardon?
We have to find it out.
HI.
HI.
Okay.
So 1 by HI plus DO by DI plus RF DO by DI plus DO by 2K, because pi and L will cancel out, plus 1 by HO. So this is the equation. Okay. So we are asked to find out what this UO. But what are the things given here? So DO DI, we know RF is given, K is given, and HO is also given. So the question we have in the question, we have to find out what is HI. That is the convection coefficient inside the tube. Okay. So that is the task here. So each tube means the total is given 4,000 kilogram per second. Okay. So mass flow rate of each tube is how much? 400 divided by, there are 1,000 tubes. Okay. So we are assuming that it's equally distributed. So 0.4 kilogram per second is the mass flow rate through a single tube. So what is the Reynolds number? 4 m dot divided by pi di mu. So di, so mu and all is given. So 4 into what is mass flow rate? 0.4. Pi into di is 25. What is mu? 9.60 into 10 raised to minus 4. So can you please calculate what is the Reynolds number of the flow?
So 21231.
Yeah, 21231.4. So this is a turbulent flow. Okay. So we already in the previous convection in the flow through a tube, we already studied the correlation, which is the Ditterboiter correlation for a flow, turbulent flow through an internal tube. So what is this correlation? Nu Nusselt number is equal to 0.023. Reynolds number is to 0.8. Prandtl number is to zero point 0.4. Okay. So from it we will get the internal heat transfer coefficient, which is K divided by DI 0.023, Nod's number is to zero point 0.8, Prandtl number is to zero point 0.4, which is equal to what is K? 11110. Sorry, it's zero point 0.4. The K of the liquid. Okay. So 0.6 divided by 25 into 10 raised to minus 3 to 0.023. The Reynolds number is 2123.4 raised to zero point 0.8. Prandtl number of the liquid 6.66. So this will give the heat transfer coefficient, which will be around 3399 watt per meter square Kelvin. So this calculation you can do later. So now it's easy to solve the question. I think now you understood, because uh, you have to apply the principle of internal flow also in this question. Okay, it's not like uh, every section is independent. So there can be combination from the combinations also. We can expect these kind of questions in the course examination. So yeah, so our basic task of finding out the internal heat transfer coefficient is over. So now just substitute the equation, equation number one. So 15339 into do minus di plus do by di. What is RF? 10 raised to minus 4. Yeah, 10 raised to minus 4 plus do F2 into K. Here, here K is water or the brass, or the thermal conductivity of tube. This K,
So can you repeat what
this
you're
K,
telling?
this K. What is this K? Means whether K thermal conductivity of water or the brass tube.
Metal.
Yeah. So I think it is given as 110 into ln 28 divided by 25 plus outer heat transfer coefficient is given 10,000. So if you take the inverse, you will get around 1,800 watt per inch square Kelvin. Okay. So I hope this question was clear. So the only part was to find out this HI. The rest of thing is almost same. So this is a correlation for turbulent flow. For flow through an internal pipe, the Reynolds number is turbulent. Okay. So let's move on to the next question. So we have a cold water enters at a counterflow heat exchanger at 10 degrees Celsius at a rate of 8 kilogram per second, where it is heated by hot water stream that enters the heat exchanger at 70 degrees Celsius at a rate of 2 kilogram per second. Assuming the specific heat of water to be remain constant, value of this, determine the maximum possible heat transfer rate. We can just try solving this question. I will be back in 2 minutes. You got the answer?
I think B is the answer, sir.
Yeah, B is the answer. 502 kilowatts.
Actually,
Yeah,
I'm getting 501.8.
okay, that's fine. So first here, what we have to do is we have to find out what is the maximum possible heat transfer. Okay, so when the maximum possible, uh, what are the given things? So first one is cold fluid enters at TCI is given, so 10 degrees Celsius, and the mass flow rate of cold fluid is also given. Heated by a hot water stream that enters the heat exchanger at 70 degrees Celsius at equal to 2 kilogram per second. Okay, and this is the uh, given conditions. So, what is the maximum possible heat transfer that can take place in a heat exchanger? Can you tell? Means
Sir, when
I'm saying,
the heat capacity rate is the minimum and the temperature difference is maximum.
yeah. Basically, if you think the cold fluid will attain the which one? The cold fluid will rise to the inlet temperature of the hot
Hot
fluid.
fluid.
That's the
Yes, sir.
maximum heat transfer that can happen, right?
Yes, sir.
When the heat capacity is minimum, at the minimum heat capacity. So in this case, so for maximum heat transfer, that is Q max happens when the heat capacity is minimum and the maximum temperature difference takes place. Okay, THI and TCI, or you can write in the reverse way also. So in this case, what is the heat capacity of cold fluid? That is MCCPC. Both are water, right? So it's 8 into specific heat, and CH is MHCP, that is 2 into CP. So what is C min? Which is the heat capacity of the hot fluid. So Q max is equal to MHCP THI minus TCI, which is equal to 2 into 4180 into 70 minus 10 is equal to how much? Almost 502 kilowatts. So I think you also did like this, right?
Yes, sir.
Yeah. Okay. Then we will move on to the next question. We have water with the CP given and which enters at 80 degrees Celsius. There's a counterflow heat exchanger with a mass flow rate of 0.5 kilogram per second. Air enters at 30 degrees Celsius with a mass flow rate of 2.0 kilogram per second. So it's basically water is losing heat and the air is gaining heat. If the effectiveness of the heat exchanger is 0.8, what is the LMTD of this heat exchanger? So what is effectiveness of a heat exchanger?
Sir, heat exchange divided by maximum heat exchange,
Yeah,
Qmax.
yes, yes, right. So can you please try this? Please try and let me know the answer. Did you got the answer?
No, sir.
Okay. So we have a heat exchanger. So water is exchanging heat centers at 80 degrees Celsius, and it's a counterflow heat exchanger, 30 degrees Celsius. And okay, these are the given things. So then what is the specific capacity of cold fluid? cold fluid here is air. Okay, that is mass of air times Cp of air, which is what is mass of air 2.09 into 5. I'm approximating it point
2.1.
2.1 kilogram per second. What is the hot fluid? That is mass of water Cp of water. That is zero point 0.5 into what is this answer?
So that is also 2.1.
It's also 2.1. Okay, so the both are same, right? The specific these are same. So what is the effectiveness? U Q actual divided by Q maximum possible heat transfer. What is Q maximum possible heat transfer? C mean. As both are same, you can take anything, C, anyone, Cc or Ch times Thi minus Tci, right? Which is equal to 2.1 into Thi is 80 minus 30. What is this answer? So
100.
this you have to convert to, this is in kilojoule. You have to convert to joule. You have to multiply by 1000. Okay. So you will get the answer in kilowatts. So what is the answer?
100.
100.
100.
I am getting almost like this. Okay. Maybe some slight difference is there because I have taken 2.09 as the capacity. Okay. This is the maximum possible heat transfer. So what is the Q actual? Effectiveness into this work, right? Equal to zero point 0.8 into 104.5. So this will be around, okay. So this is the actual heat transfer in the heat exchanger. So what is our question? We have to find out the LMTD. So what is the LMTD? So as the heat is just a counterflow heat exchanger and also the heat capacities are same. So what is the LMTD? As Cc is equal to Ch. The LMTD is equal to either delta Ti or delta Te. That I already told in the first. So this is equal to Thi minus this is this is Thi, this is Tho, this is Tco, this is Tci. Is equal to Thi minus Tco, which is the one we have to find out. Okay. So is equal to so what we know here is THI. So we have to find out what is THO. So how to find it out? How to find out TCO?
From effectiveness.
You can just have the energy balance. You give, you know the actual heat transfer. You know the specific heats. Okay. So we have is equal to, as TCO is, we are we need to find out C of cold fluid times TCO minus TCI. So which is TCI is equal to 83600 divided by what is CC into, sorry, plus what is inlet temperature of cold fluid 30. What is this answer? around
69.8.
yeah 69.8 degrees Celsius. You can say it's actually 70 degrees. Okay. So what is LMTD? So now we got everything. That is THI minus TCO is equal to what is THI 80 minus 70, which is equal to 10 degrees. Actually, where you got stuck means I hope this question is clear.
Yes, sir.
Okay, let's move on to the next question. So in this question, we have a parallel flow heat exchanger operating at steady state conditions. The heat capacity of hot and cold fluid are equal. The hot fluid flowing at is at 1 kilogram per second and with a specific heat of 4 kilojoule per kilogram Kelvin enters the heat exchanger at 102 degrees Celsius, while the cold fluid has an inlet temperature of 15 degrees Celsius. The overall heat transfer coefficient is estimated to be 1 kilowatt per meter square Kelvin, and the corresponding heat transfer area is 5 meters square. We have to find out the exit temperature of the cold fluid. We may please try after that. So Have you got the answer?
No, sir.
So here we have a parallel flow heat exchanger. Okay, so the heat capacity of the hot and cold fluid is equal. So Cc is equal to Ch. This is heat capacity, that is the product of mass and specific heat. Okay, and the hot fluid flowing at the 1 kilogram per second with a specific heat enters the heat exchanger at 120 sorry 102 degrees Celsius, and while the cold fluid has an inlet temperature of 15 degrees Celsius. So this is THI, TCI, THO, TCO. And the overall heat transfer coefficient is estimated to be, that is U is given, that is 1000 watt per meter square Kelvin, and the area is also given. You have to find out what is the exit temperature of the cold fluid, that is you have to find out TCO. Okay, so here both the none of the exit temperatures are given. In this case, we have to we cannot directly find it out, right? Here we cannot use the energy balance also. So here we have to use the NTU effectiveness method. So what is the effectiveness? NTU method, that is effectiveness is equal to 1 minus, this is for a parallel flow heat exchanger, NTU 1 plus CR divided by 1 plus CR. CR is the ratio of C min by C max. That is the ratio of the heat capacity, which is the ratio of the minimum heat capacity to the maximum heat capacity. So here what is the CR? What is CR here?
1.
Yeah, because it's already given the heat capacities are same. So the effectiveness is equal to 1 minus e raised to minus NTU times 2 divided by 2, right? What is NTU? That is the heat transfer unit, which is UA divided by C min. Okay, UA is given, that is 1000 into 5 divided by C min is C min, both are same. So we can either take hot fluid. The hot fluid is given, that is 1 kilogram into 4 kilogram kilojoule per second. So it is 1.25. So the effectiveness is equal to 1 minus C raised to minus 1.25 times 2 divided by 2. So can you please calculate what is the effectiveness value?
Point 215.
Point?
0.215.
No, no. I'm getting what is e raised to minus, that is 1.25 into 2 is 2.5. So what is e raised to minus 2.5?
0.573.
0.573. Let me visualize. It's 0.082, right? 1 minus 0.082 by 2. The effectiveness is around 0.459. You can just recheck the calculations. I am getting this answer. So we got the effectiveness. So what is the actual heat transfer effectiveness into Q max is equal to effectiveness into C min into THI minus TCI is equal to 0.459 into C min is 4000 into that is THI is 102 minus 15. So this will come out to be around watts. Okay. So what is the actual question? We have to find out the exit temperature of the cold fluid. Now you can just use the energy balance, right? 1597 is equal to the, because both the heat capacities are same, so you can use 4000 itself, and TCO minus TCI. TCI is 15, so if you calculate, you will get TC was around 55 degrees Celsius. I hope this question was clear.
Yes, sir.
So we'll move on to the next question. So we have a counter flow double pipe heat exchanger is used to heat water from 20 degrees Celsius to 80 degrees Celsius at a rate of the mass flow rate is given 1.2 kilogram per second. Mass flow rate. The heating is to be accomplished by geothermal water available at 160 degrees Celsius at a mass flow rate of 2 kilogram per second. The inner tube is thin walled and has a diameter of 1.5 centimeters. If the overall heat transfer coefficient of the heat exchanger is 160 watt per meter per Kelvin, determine the NTU and the length of the heat exchanger required to achieve the desired cooling. In this question, what we are given is we have a heat exchanger, counterflow heat exchanger. So the hot fluid, the cold fluid enters at 20 degrees Celsius and uh, yeah, it's 20 degrees Celsius and it is to be raised to 80 degrees Celsius. And the heating is to be accomplished by geothermal water, which is at 160 degrees Celsius. So the exit temperature is not given. Okay. And the mass flow rate of the cold fluid, that is C, is equal to 1.2 into 4.18, which is equal to, okay, let it be here. And mass flow out of hot fluid, that is the capacity, heat capacity, AC and CH, equal to 2 into 4, 4.31. Okay. So we are asked to find out what is the NTU. So for NTU, it's like counterflow heat exchanger. So that is we have to, what is the normal formula is UA by C min. So here the area, what is the length is not given, and the area of heat exchanger is also not given. So we have to find out we have to depend on the N2 effectiveness relationship. So I'm just directly writing. Okay. So this is the N2 effectiveness relationship. So for a counterflow heat exchanger, so what is CR? C min by C max. Okay. So what is this answer? It is CC, that is the cold fluid is around 5016, and this is 8620. So what is C min by C max? What is C min by C max? That is CR around
Point five eight.
0.588. Okay. If you substitute here, yeah. So what we need here, the epsilon. So can we find out epsilon? What is epsilon? Epsilon is equal to Q actual divided by Q max. We can find out Q max, right? So Q actual. How? By the energy balance of this cold fluid. So what is the 5016? That is Q actual, that is a cold fluid, minus temperature difference, 80 minus 20. It is the maximum possible heat transfer. That is C min. Here the minimum is the cold fluid itself into the maximum possible heat transfer. That is THI minus TCI, right? Is 160 minus 20. What is this? That is 60 divided by around 0.4285 is the effectiveness. So just substitute here. N2 is equal to 1 minus 0.58 minus 1 ln 0.4285 minus 1 divided by 0.4285 into CR is 0.58 minus 1. Okay. So if you solve this answer, you will get the NTU was around 0.651. So you can solve this later. So now you got a NTU. So the first question you got NTU, and we are next is the length of the heat exchanger. So what is the definition for NTU? That is UA by C min. So this is equal to, so from this we can find out area, which is equal to NTU into C min by U, which is equal to 0.651 into what is C min 5016 divided by U is already given, right? 640. So this is equal to 0.651. It is around 5.1 meters square. So from that, then you can easily find out what is the length. That is area is equal to pi dl. So hence L is equal to 5.1 divided by pi into d is given, right? Yeah, 1.5 centimeter. So the length will become around 108 meter. So this was a similar question of earlier time. So I hope this was clear. Okay. Now we will move on to the next question. So we will skip this question because this is of similar kind. So we will go to the ninth question. Then at last we will sort. So in this question, we have a single pass one tube pass counterflow heat exchanger, which has 10 tubes with dimensions around 10 mm and outer diameter 12 mm respectively, and a length of 1 meter. Saturated dry steam enters the cell side at a flow rate of 2 kilogram per second and temperature 100 degrees Celsius. In the tube side, cold fluid enters at a flow rate of 10 kilogram per second with an inlet temperature of 25 degrees Celsius. The overall heat transfer coefficient based on the outer surface area is 50 kilogram per second. The specific heat of water is given, a latent heat of steam is also given. We have to find out what is the exit condition of the steam. It's like it's exchanging with the steam. So saturated steam is entering at one side, and steam with some quality. That is what we have to find out. Is exiting. That is the hot stream, and the cold stream it's water, and the outer diameter and inner diameter and outer diameter is given, and the overall heat transfer coefficient is also given, and the surface area of the outer surface area of the tube is given, and the specific heat, latent heat of steam, all are given. So what you have to find out is what is the exit quality of the steam. Okay. So actually, if the exit temperature of the cold fluid was given, then it was easy because we will get what is the heat transfer rate, that is heat gained by the cold fluid, and we can just equate with the change in the enthalpy of the steam. But here that is not given. So we have to go to the what into effectiveness method itself. So first the area is given, that is area of a single tube, that is pi dl, which is equal to uh, how much is the diameter? Yeah, pi into d means its outer area is given. So outer diameter is 12 into 10 raised to minus 3 into length is 1. So this will come out to be around 0.03768. This is the area of a single tube. Okay. So NTU is equal to U0 A0 divided by C min. This is U0 is given how much? 50 kilowatt. 0.03768. What is the mass flow rate of single tube. Of a single tube, 10 tubes are given. So what is the inside tube? Water enters it. Okay, 10 kilogram per second is the total uh, flow that is to the 10 tubes. Okay, then we have to divide by 10. So the 1 kilogram per second into what is the specific heat? 4180. So what is this NTU? So it will come out to be around 0.45. So what is the what is the C max here? C max is it's like some phase change is happening at the other side. So what is the specific heat of during phase change? It's infinity. So the C max in this case is infinite. So what is CR? C mean by C max, right? So C max is there and C min is there. C max tends to infinity. So what is CR?
0.
Yeah. So it's 0. So what is NTU? This is a counterflow heat exchanger. So if you substitute this CR is equal to 0 here, you this expression will reduce to what? N2 is equal to minus ln 1 minus epsilon. Okay. Or we can say,
Sir, can you please explain why this C max is infinity?
because in that, what is the expression for C? It is mass into the specific heat. What is the
Yes,
specific heat for during a phase change?
0.
0. No, no.
No, infinity.
It's infinity. That's how it becomes infinite. I hope you understood.
Yes, sir.
Yeah. So if you rearrange this, you will get epsilon is equal to 1 minus e raised to minus NTU is equal to 1 minus e raised to minus what is NTU minus 0.5. So this is equal to, it will come out to be around 0.3623. Okay. So we got epsilon. What is our question? We have to find out the exit condition of the T. Now, what is the actual heat transfer? That is Q epsilon times Q max. That is epsilon times C min into what? TCI minus T, THI minus TCI. That is 0.3623 into C what is, yeah, it is C min is how much we found out? 1480. So this is I am taking the total heat. Total heat. Okay, total heat transfer rate. It's not for a single tube. So I am multiplying it with 10 tubes. Okay. So this is the NTU for a single tube. So the actual total heat transfer coefficient for the entire inner tube is we have to multiply it by 10. This is equal to 100 minus 25. So this will come out to be around 1135810.5 watts. This is the actual possible actual heat transfer. Now we have to do the enthalpy change for steam. So the enthalpy, inlet enthalpy at inlet for steam is equal to m dot hfg. Okay, this is sorry, it is saturated steam, right? So it is the vapor enthalpy. Now the enthalpy at exit, it is with some what quality, which is equal to hg plus x times hf. Some quality is there. So if you expand this, you'll get m dot s is equal to hg plus x times hf minus hg minus hf is equal to m dot into hg plus x hg minus x hf. If you what is the change in the heat transfer? Means what is the enthalpy change? Which is equal to the change in enthalpy of the steam is the heat gained by the water. That we already find out. So what is enthalpy change? 2 minus 1, which is equal to m dot s hg plus x hg minus x hf minus hg. Okay, am I right?
Yes, sir.
Yeah, this is not hg, this is hf. Okay, yeah, right. So m dot s is equal to, if you combine this, you will get hfg minus x times hfg. What is hfg? hg minus hf. Okay, this is equal to m dot s into 1 minus x times hfg. So this is the change in the enthalpy of the steam. So you can just equate these three is equal to this one. So m dot s is equal to 1 minus x. hfg is equal to how much? 1135810.5. So from this you can, because m dot s is given, right? So the mass flow rate of steam is given to 2 kilogram per second, and hfg, that is the latent heat of steam, is 2500 kilojoule per kilogram Kelvin. So if you calculate, you will get the exit quality as 0.7728, close to this. The only thing here is you just need to know the properties of steam, the exit enthalpy, how to calculate this. Okay, I hope this question was clear. The only thing as I told, is to understand is you have to find out the change in enthalpy of the steam. That's all. Okay, I will move on to this next question. So we have a 2 shell pass and 4 2-pass heat exchanger, which is used to heat glycerin from 20 degrees Celsius to 50 degrees Celsius by hot water, which enters the thin walled 2 centimeter diameter tube at 80 degrees Celsius and leaves at 40 degrees Celsius. The total length of the tube is of the heat exchanger is 60 meter, and the convection heat transfer coefficient is given, and the determine the heat rate of heat transfer without fouling. That is the question. Okay. So in this question, it's here. I will draw the schematic. It's a 2 shell pass and 4 2-pass heat exchange. So this will look something like this. 2 shell pass. This is the shell side, and the 4 2-pass is so similar to this. So this is not like a normal heat exchanger that we have discussed till now. It's like it is going through multiple times and all. So for that, it's not, we cannot simply use what we have already done. For that, you have to use this change of correction factors. Basically, you will get this. So this chart you can find in any heat transfer textbooks. This I taken from Central heat transfer by UNS Central. Okay. So first, what you have to find out is the heat transfer Q is equal to UAF. That is the correction factor. What is delta TM? That is the normal LMTD that you have discussed. The only thing you have to do is you have to find out this correction factor. For that, you can make use of this kind of charts. So actually, I am just connecting our question with this graph. So our T1 is, it's a 2 shell pass and 4 tube pass. Okay. And is used to heat glycerin from 20 degrees Celsius to 15 degrees Celsius by hot water, which enters the thin wall tube of 2 diameter and leaves at 40 degree. So this is 20 degree. Okay. And leaves with 50 degree. This is the shell side. And the tube side, it's saying that the uh, 80 degree and 40 degree. This is the entering point. So this is how much? 80 degree and leaving it with 40 degree. So what you have to find out is we have to our objective is find to F. So what is R? T1 minus T2 divided by T2 minus T1. What is T1 here? 20 minus T2 50. T2 is 40 minus 80. What is this answer? Is around 2 by 3, which is equal to 0.6667. Okay. Next parameter we have to find out is P. P is T2 minus T1 divided by T1 minus T1. Okay. This is P value. What is T2 here?
No,
40 minus
sir, this R should be 3 by 4.
3 by 4. Okay, fine. Yeah. So this is 30 by 40. Yeah, 3 by 4. It will come out to be around 0.75. Yeah. So this P, I think P, what is T2 minus T1 by T1 minus T1? So T2 is 40 minus T1 is 80 divided by T1 is 20 minus small t1 is 80. So this is minus 40 by minus 60. So this is 2 by 3 is equal to 0.6667. Okay. So now you can plot. So first one we will take P, which is 0.6667. This is close to here. Okay. This is P, and what is R? 0.75. So this is 0.8 and 0.6. So in between 0.7. So it will be close to some graph like this. We can take. So this will be close to around 0.91. That is the correction factor. So while using graph, there will be some difference. Means when you calculate, it will be 0.92 or 93. So that is acceptable, not that too much. Some tolerance is acceptable while using these graphs usually. So, but not more than some 20 or 30%. Okay. So the F we found out. So now the LMTD, that is delta Ti minus delta To divided by Ln delta Ti by delta To. Okay, is equal to 30 minus 20, that is delta Ti inlet That is okay. So what is delta Ti? Delta Ti is equal to Th in minus Tc out equal to 80 minus 50 30 degrees Celsius. Tho minus Tc is equal to 40 minus 20 equal to 20 degrees Celsius. So this will be from 30 minus 20 divided by ln 30 by 20. You will get around 24.60 degrees Celsius. So now there is no fouling, and as it's asked to take a thin wall tube, so there is no need of considering the uh, what the conduction resistance. Okay, now you can just take the inverse, that is 1 by u is equal to 1 by hi plus 1 by ho. So that is equal to 1 by 160. Sorry, yeah, convection heat transfer. First, you have to find 1 by 60, 1 by 1. What is 1 by ho? 25. You will get u is equal to 21.612 watt meter square. So now just substitute UAF delta Tm equal to area of tube is how much? Pi into 2 into 60. 0.91 into this delta Tm 24.6. This answer will come out to be around. So this kind of questions means like you need some chart or something. So usually unless you are provided with chart, you cannot do this kind of question. So uh, I just want to introduce you to this kind of how to use these charts. That's why I have taken this question. So just to know. So if you refer back to some textbooks, you can find more questions related to this. Now, I think we left one question. Okay, this one. Two fluids A and B exchanges heat in a counterflow heat exchanger. Like fluid A enters at 420 degrees Celsius and has a mass flow rate of 1 kilogram per second. Fluid B enters at 20 degrees Celsius and also has mass flow rate of 1 kilogram per second. The effectiveness of heat exchanger is 0.75. Determine the exit temperature of A and B. So I think you will be able to do this. I will just give how to solve. The rest you can uh, do it as a homework. So we are given the hot fluid A enters at 420 degrees Celsius. It's a counterflow heat exchanger. And fluid V enters at 20 degrees Celsius. The effectiveness is given 0.75, so which is equal to Q actual divided by Q max. So you can easily find out what is Q max. Okay, that is TCHI and TCI are given, and the you can find out what is CC, that is cold fluid, which is a fluid A, right? Fluid B, which is uh, 1 into 4, and CB is a hot fluid, that is 1 into 1. A is, yeah. Then you can find out what is the Q min, that is the T min, and from that you can get the actual heat transfer. So after getting actual heat transfer, you can just use the energy balance of hot and cold fluid to get the inlet and exit temperature. Okay, that's also a simple question. Okay, now we come to the end of our session. Actually, this will be our last class because the course is over. So when is your exam?
Pardon?
When is your online exam for this course?
Yeah, it is very good, sir. I have revised it and everything.
Yeah. So when is it? Means the date. The date of the examination. Online exam.
That is on Sunday.
Coming Sunday. Okay. So
Sir,
I hope.
sir,
Yeah.
one thing I want to ask, that you wrote that balance equation for uh, EI minus EO plus E generation, right?
Which
In the
one?
beginning of the lectures, now we applied the heat balance, then the heat generation is there. That EI minus